equilibrium law. So let's say we had a reaction of A plus B, and we are using the capital letters to represent the species and the little letters to represent the coefficients that are in front of those species. So we have A plus B forms C plus D. We could write the rate law for this reaction. So for the forward reaction, we'd be looking at our K value, lowercase k, would be the concentration of A with a particular exponent and the concentration of B with a particular exponent. We could also look at the rate law for the reverse reaction. So if we wanted to go backwards for this particular reaction here, we could write the rate law in terms of what was a product, C, raised to its exponent, and D, the other product, raised to exponent. But remember, if we're going backwards, they're not really products anymore. We're treating them like they are reactants. So we're moving backwards to this reaction. So this is what the reverse rate law would look like. Now, at equilibrium, we know that the forward reaction and the reverse reaction, the rates of those two, are going to be equal. That's the definition of equilibrium, is where the amount of the forward reaction is equal to the amount that is going through the reverse reaction. And it is strictly talking about the rates of those two reactions. So as much product is being produced as products are being turned back into reactants. That's what's happening at equilibrium. So what we can do is we can set up the reaction so that if the rate of the forward reaction equals the rate of the reverse reaction, then we can substitute those two equations into each other. And we can derive this equation. We can say, okay, well then, if the rates are equal to each other for the reverse reaction, then the rate constant for the forward reaction is multiplied by the reactants raised to their coefficients is equal to the rate constant for the reverse reaction multiplied by the products raised to their exponents. And we can rewrite this. Let's get this a little bit easier to see. So we put the two rate constants on one side. And so we'd end up with this equation where we have rate constant 1 divided by rate constant 2 is equal to the products raised to their exponents divided by the reactants raised to their exponents. Now, since we have these two constants here, they're numbers, they're constants, they're by definition not changing. So instead of writing out two separate constants that never change, we can just actually write them as a single constant. And this is where that capital K is coming from. So, quick note, we said when we talk about the rate law expression, the coefficients in the reaction are not necessarily the exponents in the rate law, and that is true. However, for reasons that we're not going to get into the details of, when we're at equilibrium, essentially that will always hold true. Essentially the mechanism is going to work out for the forward mechanism, and the reverse reaction will work out that the coefficients will work out as the exponents as long as you are at equilibrium. It would not be true if you're not at equilibrium, but at equilibrium those coefficients will be the exponents for the reactants and the products. So what we end up with is, for this reaction, putting it all together, we get what's called our rate law equation. So we have this new constant, capital K, and it is equal to the products, the concentration specifically of the products raised to their exponents, divided by the concentration of the reactants raised to their exponents. And however many products there are and how many reactants there are, you put them into the equation. Realize that sometimes this might be written as Kc or Keq, whatever you want to label it as. Refer to this as being the rate constant, K. Put whatever subscript you want on it. It is the products raised to their coefficients divided by the reactants raised to their coefficients. All right, so what this is, if the equilibrium concentrations are known, we can figure out what K is. So you take out, you plug in their concentrations at equilibrium, you use the coefficients as the exponents, and you'll be able to find out what K is. Realize the K for a reaction, and it's the reaction as written. So when you decide to write a reaction, you put the reactants on one side, the products on the other side. Being as this is equilibrium, we can have the reaction go backwards just as easy as we can have going forward. So it really is dependent on how you write it. But if you, whatever you put on the left-hand side, we're going to refer to it as the reactants, and whatever ends up on the, I think I said left-hand side, whatever ends up on the right-hand side becomes the product. So it is as written, but realize because this is equilibrium, we can go forward as easily as we can go backwards. So the K of the reverse reaction will be the reciprocal of the K for the forward reaction. K is going to give us information about the position of the equilibrium. So it doesn't tell us anything about right now, because remember that the rate of the forward reaction is equal to the rate of the reverse reaction. That's what's happening at equilibrium. But what K is going to tell us is the position, and we're going to try to figure out what that means exactly, but essentially how much the reaction has gone either towards the product side or how much is left as reactants. It is also going to vary with temperature as well. So when you change the temperature reaction, you're also going to end up changing the K value. So K tells us about the ratio of the reactants to the products and the concentration of them, how much you have present. If K is large, what that means is, because think of what K equals, it's products over reactants. So if the number is large, that means that the numerator must be greater, and so that must mean there are more products. If K is small, again, that's the reactants are on the denominator, so if there's more reactants, K would end up being small. It's saying that the reactants are favored. And what we mean by whether one's favored or the other is how much is there of one or the other. If a reaction goes completely to completion, goes 100% towards the products, then we'd say, okay, the products are definitely favored. It made nothing but products. If the reaction only starts off and goes a little bit, then there'll be lots of reactants still when it hits equilibrium. And so we'd say, okay, the reactants are favored. So essentially it is how much products have you produced from the reactants, and which one is there essentially more of. If it happens to work at equal, then it shows that the concentration of the two are about equal. But remember that's not terribly important, because that's not what equilibrium is. Equilibrium is not when the amounts of reactants is equal to the amounts of product. That's not equilibrium at all. Equilibrium is when the production of products is equal, the rate of production of products is equal to the rate of production of reactants at any amount. So heterogeneous equilibriums, when we have a solid or a liquid substance, we know that their concentrations can't change. They remaining constant. So for example, what is the concentration of liquid water? It's 55.5 moles per liter. That is the concentration. That's how many, if you had a liter of water, there would be 55.5 moles of water in there. So that is its concentration. And it essentially does not change. You can't really compress it. You can't expand it. So the amount of water within a given volume should remain almost entirely constant. Same thing with any solids. So since the concentration of liquids and solids is itself constant, they're just another constant value that's in an equation. So they get incorporated into the K constant. We don't want to have two constants in the same equation. So essentially, if we have a constant concentration, it's incorporated in with the K value for that reaction. So for example, if we were to take water and we were to decompose it to give hydrogen and oxygen, if we're starting with liquid water, its concentration will not change. So we could write the K expression for this, and K is the products over the reactants, and we use the coefficients as exponents. So we would have the concentration of the oxygen multiplied by the concentration of hydrogen, and hydrogen has a coefficient of 2, so we're using that as the exponent on hydrogen. Now water would be a reactant. It's on the bottom here, and there's a coefficient of 2. But what's important is that this water, its concentration does not change. It is a liquid. It must remain constant. And instead of having two different constants in an equation, essentially we eliminate this constant, or we incorporate it into the already constant value for K. So anytime you have a liquid or a solid, they're not going to show up in your K expression. And so the K expression for this reaction is just going to be the concentration of oxygen multiplied by the concentration of hydrogen squared. For ionic substances, each ion must be written into the equilibrium expression. So essentially we have to write the net ionic equation that we're dealing with, make sure it's balanced, and then write those ions in as if they're their own species, which they are. assuming they are aqueous, write them in with their particular coefficients. So for example, writing the equilibrium expression for lead 2 nitrate reacting with potassium iodide. So first off, you can pause this and try to write the net ionic equation for this particular reaction. The chemical equation will look like so, and again, if it is ionic and it is aqueous, what that means is that those ions are not actually together, they are separated. So when you go to write your net ionic equation, lead 2 nitrate is actually a lead 2 ion and 2 nitrate ions separated, floating around in water. The potassium iodide is going to be 2 potassium ions and 2 iodide ions floating around separately from each other. Lead iodide is solid, so we do not separate it. Remember, the things that we write as separate ions are going to be, they have to be both ionic and aqueous. Lead 2 iodide is only ionic. It is not in its current state aqueous. And then the potassium nitrate also gets broken up into its ions. Cancel out the spectators, so the ions that are not doing anything. The potassium ions are just hanging out. The nitrate ions, there's 2 of them. They're at the beginning, they're at the end, so they're really not doing anything either. So really, essentially what we have is a lead 2 ion that's floating around in water, 2 iodide ions that are floating around in water, and they come together to form our solid lead 2 iodide. So when we go to write our equilibrium expression for this, again, it's products over reactants. So we would have K is the products, but of course this is a solid, and so its concentration does not change. So instead of putting the concentration of it up here with the PbI2, since that is a constant number, we do not include it written into the equilibrium expression because it is already included in with the K value. So we put a placeholder of 1 to represent the products, and then we have the reactants written on the denominator raised to the coefficient in front of them being used as the exponent. So there's our equilibrium expression. Now, if you don't like fractions, which I don't think anyone does, we could say that we could reverse this reaction and write it the other way. And we could say, okay, if we're going to put these guys on the left-hand side, the products, and we could write them as reactants, and write the reactants as if they were products, then we would have the reciprocal value for the K expression. Now realize the K in that case would be not the same K, would be the reciprocal of the first K here. And so dependent on how the reaction is written, you have to express how the reaction is, you have to write it out, and then your equilibrium expression will apply to how that reaction is written. If you decide to flip the equation around, you're going to have to also flip your K expression around as well.